Hi, this week we will do an experiment on rotational motion. The goal of this experiment is to determine the moment of inertia of different objects. For objects at static equilibrium, sum of all forces and sum of all torques acting on the object are zero. This means that translational and angular acceleration are equal to zero. For the case when sum of all forces is equal to zero and sum of all torques is different than zero, the linear acceleration is equal to zero, but the angular acceleration is different than zero. Linear acceleration depends on the force applied to an object and on the mass of the object, while the angular acceleration depends on the applied torque and the moment of inertia. The torque is a moment of force. It is the tendency of object to rotate about one axis when the force is applied. By definition, torque is a cross product of R and F. Or if we look at the magnitude of the torque, torque is equal R times F times sine theta, where R is a lever arm. It is the distance from the axis of rotation to the point where the force is applied, and the angle theta is the angle between lever arm and the force. Units for torque are Newton meters. Moment of inertia is a mass property of rigid object that depends on the torque needed so that object will attain desired angular acceleration about an axis of rotation. It depends on the shape of the object, the mass, and it is different around different axes of rotation. On this example here, you can see that for this rod here, the moment of inertia is different because we change the axis of rotation. For this example here, the axis of rotation is at the center of this rod, and for this example here, the axis of rotation is at one end of the rod. And then consequently, moments of inertia are going to have different equations. For the one where the axis of rotation is at the center, moment of inertia is the mass of the rod, length squared divided by 12, and for the rod whose axis of rotation is at one end, the moment of inertia is given by this equation, ml squared divided by 3. The angular motion of object is described by its angular displacement theta, the angular velocity omega, and angular acceleration alpha. The average angular velocity is a change in angular displacement over a period of time, and average angular acceleration is a change in angular velocity during the period of time. The connections between linear and rotational quantities are given by this equation. Tangential velocity is r times omega, and tangential acceleration is r times alpha, where r is the radius of trajectory, or in this case it's going to be a lever arm or the length of the object. The Newton's second law for rotational motion is described by this equation. The total torque on the object that rotates is equal to its moment of inertia times the angular acceleration of the object. Recall that the moment of inertia is the measure of rotational inertia. The units for moment of inertia are kilogram meter squared. The moments of inertia for objects used in this experiment are given by this equation. Moment of inertia for horizontal disk is 1/2 mass of the disk radius squared. Moment of inertia for vertical disk is 1/4 mass of the disk radius squared. And moment of inertia for the ring is 1/2 mass of the ring inner radius squared plus outer radius squared. Let's now talk about experimental setup used for this experiment. On your table, you're going to have setup like this. So on your rotational base, here is the pulley, and here is the sensing wheel. You will have a photo gate here that will record the velocities for this pulley. Then across this pulley here, you have a falling mass m down here, and then rotating object will be mounted on the top of this base. Mass of the pulley is neglected, but the friction force will be measured using the conservation of energy. So first, let's draw the free body diagram for the forces acting on this system. You have the gravitational force for this falling mass. You have the tension and the cord here and here, same amount. And then you're going to have a friction force in this direction opposing the motion. So now let's write down the second Newton law equations. For the falling mass, it's going to be Ma is equal mg minus tension in the cord minus the friction force. The second Newton law for rotating object, sum of all torques is equal to the moment of inertia of the object times the angular acceleration. The force is tension. The lever arm is r, is the radius of this pulley. And then the angle between lever arm and the force is 90 degrees, and sine of 90 degrees is 1. So we're going to have T times R is equal moment of inertia of this disk times the angular acceleration. Now, if we know the relationship between the linear acceleration and angular acceleration, we can solve for the moment of inertia of the disk, and we are going to get this equation. Moment of inertia of the disk is equal to mr squared times g over a minus 1 minus f divided by ma. Here, small m is the falling mass, and this r here is the radius of this pulley, and the value for the radius of this pulley will be given to you by your instructor. You will use this equation to experimentally determine moment of inertia of the rotating object on this space. The only term that you don't know from here is the friction force. To determine the friction force, we are going to use the concept of conservation of energy. Recall that the work done by non-conservative force is a sum of the change in kinetic energy and change in potential energy. Since the change in kinetic energy is zero, then the change in potential energy is going to be equal to mg delta H, and work done by non-conservative force, in your case friction, is going to be equal to this. Since we are going to start with our falling mass at some initial height, and this initial height is greater than the final position of the falling mass, we are going to get that the change in potential energy is less than zero, and we know that work done by friction force is less than zero because the friction is opposing the direction of displacement. From here, we can write that friction work due to friction force is equal to mg h initial minus h final, and that's going to be equal to the friction force times displacement. D is the total distance falling mass travels. So if we start from h initial, the mass is going to travel down to h0 and then come up to h final. So our total distance is going to be h initial minus h0 plus h final minus h0. h0 here is the lowest point the falling mass reaches. H initial is the starting point of the falling mass. This is a top point, and then h final is the final point of the falling mass, and this is this midpoint here. So then, plugging the value for the displacement back to this equation, we get the equation for the friction force, and the friction force is given by this term. It is mass of the falling mass times g times h initial minus h final divided by the total distance. In our case, is going to be h initial plus h final minus 2h0. During this experiment, you're going to record the tangential velocity of this pulley here, and then using the Data Studio, you're going to calculate the tangential acceleration. In order to calculate a tangential acceleration at any point on the rim of this rotating disk here, you need to know that since these two objects, rotating object and the pulley, are connected and they're rotating around the same axis, that the angular acceleration for the pulley is going to be equal to the angular acceleration of the rotating object. Now, knowing the radius of this pulley and the radius of your rotating object, you can easily calculate the tangential acceleration of the rotating object. Next, I will show you a short demo on how to do this week's experiment. Okay, so this is a setup for this week. We have a rotational triangular base, the photo gate that is connected to science workshop, so we can measure the tangential velocity of the pulley. We have the hanging mass, will go on the mass hanger. We have 150 and 120 gram mass, and we have this hexa key. You have a ring and a disc. So first we are going to determine the moment of inertia for the horizontal disc. Notice here that disc has this D-shaped hole, and also this post here for the disc is a D-shaped. So align the flat surface, put a disc on, and now you're going to put 100 grams on the mass hanger. So your small m now is 105 grams. So first what you're going to do is you're going to bring the falling mass to the top, and then you're going to measure the initial height. The easiest way to do this is there is this knot here to measure either to the bottom or to the top of this knot. So this is your H initial. Then you're going to release this disc and start taking data with Data Studio on your computer. So once this falling mass reaches ground, you're going to stop recording the data, but you're going to wait up until this disc is about to change the direction again here, and then you're going to measure. This is going to be your H final. Okay? Because you're recording a velocity as a function of time, and that is a tangential velocity of this pulley here, you're going to use the Data Studio, and the slope will give you the slope of the curve velocity versus time will give you the tangential acceleration of this pulley. Now, in order to calculate the friction force, you have to measure H0. H0 is the distance from the ground when the falling mass is at its lowest position. So just again, same as before, use the ruler, measure your H initial. Now you're going to use the acceleration that you obtained. You're going to calculate friction force and then calculate the moment of inertia of this disc using equation 8 in your laboratory manual. So once you're done with calculating moment of inertia for the horizontal disc, now you're going to put a ring on the top. Make sure you put a ring into the grooves of this disc here so it doesn't fly out, and then repeat the same procedure again. Bring this up, measure H initial, start recording the data, and then you're going to stop recording data once the falling mass reaches the lowest point, but you're not going to stop this. You're going to let it come up, and then just before it is about to change the direction, stop it and then measure H final. Then again, calculate the friction force, use the acceleration that you obtain in Data Studio, and calculate the moment of inertia of the horizontal disc and the ring on top of it. You know the moment of inertia for the horizontal disc, you calculated that in previous step, and then the moment of inertia of the disc ring system is equal to the moment of inertia of the ring plus moment of inertia of the disc. The last part will be to calculate a moment of inertia for the vertical disc. You have these two screws here. Please make sure that they stay there. So put the disc on. So this flat surface here is on the same side where the screw is, and then tighten it up. Now you're going to add 20 gram mass 20-gram mass to the mass hanger. Okay, and now for this step, your falling mass is 25 grams, 20 plus mass hanger, and then you're going to start your H initial is going to be at 50 centimeters. Same again, record the data up until the hanging mass reaches the lowest point, and then once disk is about to change the direction, record the H final, and then again calculate the friction force, use the acceleration you obtained to calculate the moment of inertia for the horizontal disk. Once you're done, you need to unscrew this here, take the disk off, and leave the station in exactly the same condition you found it when you walked into the lab. For the instructions to how to analyze the data, you can refer to the previous experiment, either one on the second Newton law or the one on 1D collisions. This is all for this week. Thank you.